These are the answers to the practice quiz on balancing equations and classifying reactions. In the video description area, there is a link to the packet that accompanies this video. The instructions on this practice quiz are the following. There are 15 different chemical reactions listed on this practice quiz. For each of the following reactions, balance the chemical equation using the lowest possible whole number coefficients. Classify each reaction as one of the following: synthesis, decomposition, single replacement, double replacement, neutralization, or combustion. So in the first part of this video, I will explain how each of these 15 reactions can be classified into one of these 6 categories. Then I will spend the rest of the video explaining how to balance each of these 15 chemical equations. So let's start with the first type of reaction, which is synthesis. So what are we looking for in a synthesis reaction? 2 or more substances are combined to give a single product. So we are looking for a chemical equation in which there is only one substance on the right side of the arrow, on the products side of the reaction. So on this slide, this particular reaction has only one substance listed on the right side of the equation. So this would be an example of a synthesis. We're going to use the letter S as an abbreviation for synthesis. And then on this next slide, there's another reaction in which there's only one substance on the right side of the equation, on the product side of the reaction, and that would also be classified with an S for synthesis. Now, the next reaction type after synthesis is decomposition. Now, for a decomposition, a single compound is broken down into more than one product. So now we're looking for a chemical equation in which there is only one substance listed on the left side of the equation, on the reactants side of the equation. So this equation has only one substance on the reactant side of the equation. So we'll use the letter D to classify this reaction as a decomposition. And on this next slide, I can see a chemical equation with only one substance listed on the left side of the equation. So that would also be an example of a decomposition. So D for decomposition. Now, the next type of reaction is single replacement. In a single replacement reaction, an element reacts with a compound, and the products of the chemical reaction are a new element and a new compound. So what we are looking for in a chemical equation that would be classified as a single replacement reaction would be one element and one compound on each side of the equation. Now, if you take a look on this slide at the first chemical reaction that's listed, I can see C₃H₆ and O₂ on the left side of the equation. C₃H₆ is classified as a compound, O₂ is classified as an element, but if you notice on the other side of that equation, H₂O and CO₂ are both classified as compounds. So that first chemical reaction listed there at the top of the slide, that would not be classified as a single replacement reaction. So we're looking for one element and one compound on each side of the equation. Now, the next equation that's listed involves 2 compounds on each side of the equation. So that also would not be classified as a single replacement. But this reaction involving an element, so that's chromium, an element, reacting with H₂SO₄, which is classified as a compound, is producing a new compound with a different chemical formula, Cr₂, and then parentheses SO42, but there's also a new element, so hydrogen, or H₂, is being produced. So an element and a compound are featured on both the left side and the right side of the equation, so this gets the label SR, where SR stands for single replacement. Now, is there another single replacement reaction? Let's take a look. So on this slide, we can see several different equations that have not yet been classified. And so at the top of this slide, aluminum, Al, is an element. It's reacting with a compound, which has the formula ZnCl₂, or zinc chloride. And then on the other side of the equation, we have a new compound, AlCl₃, but we also have a new element, which would be zinc, or Zn. So we've got an element and a compound on each side of this equation. This would also be classified as Sr for single replacement. And there's one more single replacement reaction on this slide. So potassium, K, is an element. It's reacting with water, which is a compound. And on the other side of the equation, the products are hydrogen, which is an element, and KOH, or potassium hydroxide, that's a compound. So with one element and one compound on each side of the equation, this would also be classified with the symbol Sr for single replacement. Okay, we've talked about synthesis, we've talked about decomposition, and single replacement. The next type of reactions that I will consider are going to be double replacement and neutralization. In a double replacement reaction, the ions of two compounds exchange places with each other, and the result is the formation of two new compounds. So what we're looking for in a double replacement reaction would be two compounds on the left and then two different compounds on the right. Now, the other type of reaction that's highlighted along with double replacement is neutralization. Neutralization involves an acid reacting with a base. So what are we looking for in a neutralization reaction? Well, one of the compounds contains H+ ions. So in the chemical formula of an acid, you normally see hydrogen listed as the first element in the chemical formula of an acid. And then a base often contains hydroxide ions, which is OH-. So if we see a compound that contains OH as an ion, then that would represent a base. So if the H+ from the acid combines with the OH- from the base, the result is a neutral compound, which is usually water. So let's go ahead and take a look at these reactions and see if we can find two compounds on the left and two compounds on the right, and then decide, is it a double replacement, or is it that specific situation involving an acid and a base called neutralization? Now, the first chemical equation that is listed at the top of this slide involving C₃H₆ reacting with O2, that represents a compound reacting with an element. So this could not be either a double replacement or a neutralization reaction. The next chemical equation listed involving K₂CO₃, which is a compound, reacting with FeCl₃, another compound, it produces two new compounds on the right side of the equation. Now let's go ahead and double check. Do we see an acid reacting with a base? Well, I do not see a chemical formula that begins with hydrogen. I don't see the hydroxide ion in any of these chemical formulas. And then I don't see water, a neutral compound, on the right. So this is just a double replacement reaction, so DR for double replacement, but it's not that more specific example of an acid reacting with a base. Let's go ahead and take a look at another one that contains a compound reacting with a compound. So magnesium hydroxide, which has the formula Mg and then OH in parentheses times 2, that is classified as a base. It's reacting with a different compound, and the first element listed is hydrogen. So HF, that would be an example of hydrofluoric acid. That's an acid. Do we have water on the other side of the equation? Yes. So therefore, that's not just compound plus compound to make two new compounds, as we saw earlier. This is a specific type of compound that contains hydroxide ions, classified as a base, so Mg parentheses OH2 is a base, reacting with a compound that contains H+ ions, where the first element listed in the chemical formula is hydrogen. That's an acid. So a base reacting with an acid to produce water. This reaction gets an N, so N for neutralization. So on this slide we can see a double replacement and we can see a neutralization reaction. Now, the last chemical equation on this slide involving a compound, C₄H₆O, reacting with O2, which is an element, that would not be classified as a double replacement. You have to have two compounds on each side of the equation. Let's go ahead and take a look at some other reactions, and we're looking for either double replacement or neutralization. So H₂S is a chemical formula that begins with hydrogen, so that would be classified as an acid. That's hydrosulfuric acid. And then the next chemical formula involving Al, or aluminum, contains OH, that's the hydroxide ion. So the H₂S, the hydrosulfuric acid, is an acid, the aluminum hydroxide is a base, and then we see water on the other side of the equation. So it is compound plus compound, but a very specific example of an acid reacting with a base to produce water. So this gets the N for neutralization reaction. In our next chemical equation, I see a compound reacting with another compound to produce two different compounds on the right side of the equation. I don't see the hydroxide or the OH minus ion. I don't see a chemical formula that begins with hydrogen, so there's no obvious signs of an acid or a base, and I don't see water on the right side of the equation, so this would be classified as a double replacement reaction. Two compounds exchanging ions to produce two new compounds. At the very bottom of this slide, I see KOH, which would be classified as a base, but I'm just going to call it a compound because I don't see an acid reacting with KOH, or potassium hydroxide. And then I don't see water on the other side of the equation. So that last chemical equation listed, although it does contain a base, it's not reacting with an acid. It's reacting with this copper sulfate compound. So we have two compounds on the left, two compounds on the right, no obvious signs of an acid reacting with a base, and I don't see water being produced. So that would be getting the label double replacement, which is Dr. Now, we've talked about synthesis, we've talked about decomposition, we've talked about single replacement, double replacement, and then that very specific example of an acid reacting with a base, which is known as neutralization. The last type of chemical reaction to consider is combustion. A compound containing carbon and hydrogen, and sometimes oxygen, acts as a fuel, and that fuel is burned in the presence of oxygen, and the products are carbon dioxide and water. So let's take a look at all of the chemical equations that have not yet been classified. Hopefully, they are going to all be classified as combustion. So here we have a compound, C₃H₆, so it's a compound containing carbon and hydrogen. It's reacting with oxygen, and the products are water and carbon dioxide. So this gets the label C for combustion. And at the bottom of this slide, we see a compound that contains carbon and hydrogen, C₄H₆O. Again, sometimes that compound will also contain oxygen. It's reacting with oxygen to produce carbon dioxide and water. So this fits the definition of a combustion reaction. Now, all of the equations on this slide have been classified into one of 6 categories. On the next slide, there's only one more equation that has not yet been classified. C₄H₆ is a compound that contains carbon and hydrogen. It's reacting with oxygen, and the products of this reaction are carbon dioxide and water. So this is our last example. This is also a combustion reaction. So we have now taken a look at all of these equations, and they've been classified as either synthesis, decomposition, single replacement, double replacement, neutralization, or combustion. Now I'm going to move on to the next part of the video where I take each of these 15 chemical equations and I will go through the process of how to balance the equation so that the same number of each element is going to appear on both the left side and the right side of the equation. Now, as I go through the process of balancing each of these 15 chemical equations, I'm going to put two tables on the slide located directly beneath the chemical equation that I'm trying to balance. And the purpose of these tables is to show you what I'm doing as I keep track of the number of each type of atom on both the left side and the right side of the equation. So right now for this equation, I see carbon, hydrogen, and oxygen. And so I'm going to start by counting the number of atoms of carbon, hydrogen, and oxygen on both the left side and the right side of the equation. So what I see on the left would be 3 carbons, 6 hydrogens, and 2 oxygens. And what I see on the right is 1 carbon, 2 hydrogens, and a grand total of 3 oxygens, because there's 1 oxygen in H₂O and there's 2 oxygens in CO2, so a total of 3. Now, we use coefficients in order to balance chemical equations. But before I place my first coefficient into this chemical equation, I need to consider which of these 3 elements might be a good element to start with. And a good piece of advice is to look for an element that is only found in one chemical formula on the left side of the equation and is only found in one chemical formula on the right side of the equation. So, for example, I'm not going to begin the process of balancing this equation by starting with oxygen. And the reason I'm not going to start with oxygen is because oxygen is found in 2 different chemical formulas on the right side of the equation. So I'm going to choose to start with carbon. So what I see is that there are 3 carbon atoms on the left, and there's only 1 carbon atom on the right. So I'm going to place a coefficient of 3 in front of the CO2 formula. Now, this 3 as a coefficient will change the number of carbon atoms and oxygen atoms on the right side of the equation. So here is my new total of carbons, hydrogens, and oxygens on the right side of the equation. So with that 3, I now have 3 carbon atoms on the right. I still have 2 hydrogens on the right because that coefficient of 3 in front of the CO2 did not affect the number of hydrogens on the right side of the equation. And as you can see in the table, I have 7 oxygens on the right. And the reason I have 7 oxygens is because with that coefficient of 3 in front of the CO2, that would be 3 times 2 for oxygen. So 3 times 2 is 6, but then there's another oxygen atom in the formula for H₂O. So that would be a total of 7 oxygens on the right. Now I'm going to try to balance the hydrogen. So I see 6 hydrogens on the left, and I would like to get 6 hydrogens on the right. So I'm going to put a coefficient of 3 in front of the H₂O because 3 times 2 is 6. So now here's my new total for carbon, hydrogen, and oxygen on the right side of the equation. So I still have 3 carbons. Now I have 6 hydrogens and a total of 9 oxygens. And the reason I have 9 oxygens on the right is because the 3 in front of the H₂O would give me 3 oxygens, and the 3 in front of the CO2 gives me 6 oxygens. So 3 plus 6 is 9. Now the only element that still needs to be balanced would be the oxygen. So I have 9 oxygens on the right. Let's see what I can do to get 9 oxygens on the left. We have a little bit of a dilemma here in the fact that 9 is an odd number, and yet what I'm looking for would be a whole number coefficient. So I can't put a whole number in front of the O2, so I'm going to use a fraction as a temporary solution to balancing this equation. Now, you could use what I did, which is 9 over 2 or 9 halves as an improper fraction, or you could also use 4.5. But the point is that now I have 9 halves, or 4.5 times 2, which gives me 9 oxygens. So take a look at the tables. You can see that we have 3 carbons, 6 hydrogens, and 9 oxygens on each side of the equation. So at this point, the equation is balanced, but the instructions say to use the lowest possible whole number coefficients. And right now, 9/2 or 4.5 is not a whole number. So what can we do to completely balance this equation using a set of whole number coefficients? What I'm going to do is multiply all 4 of these coefficients by the number 2. That way it will still be balanced, but it will get rid of that 9/2 as a coefficient in front of the O2. So the first coefficient for the C₃H₆, it's understood to be a 1. I'm going to multiply that by 2. So now that coefficient is a 2. I'm going to go ahead and multiply 9/2 or 4.5 times 2. So that becomes a 9. And then the 3 and the 3 are each going to get multiplied by 2. So now we have coefficients of 6 and 6 for the H₂O and the CO2. Is the equation still balanced? Yes, but at this point, I've doubled all of the carbons, hydrogens, and oxygens. So instead of 3 carbons, 6 hydrogens, and 9 oxygens, those numbers have been doubled. So now I have 6 carbons, 12 hydrogens, and 18 oxygens on both the left side and the right side of the equation. So at this point, as you can see, I'm going to highlight each of these 15 equations. When I balance it, I will highlight the numbers in green so you can see that the equation is balanced, and I'll put a little check mark to indicate that I'm done balancing this particular equation and I'm ready to move on to balancing the next chemical equation. So this equation is balanced, and the coefficients from left to right are 2, 9, 6, and 6. Here is our next equation, and the elements on each side of the equation are potassium, carbon, oxygen, iron, and chlorine. Let's count how many of each type of element we have on both the left side and the right side of the equation. So on the left side of the equation, I see 2 potassiums, 1 carbon, 3 oxygens, 1 iron, and 3 chlorines. And on the right side of the equation, I see 1 potassium. Now, there's actually 3 carbons because there's 1 carbon inside parentheses. The CO3 is inside parentheses, and there's a 3 on the outside. So that makes 3 carbons. And there's 3 oxygens inside the parentheses, but then that's being multiplied by 3 on the outside of the parentheses. So 3 times 3 is 9 oxygens. There's 2 irons and 1 chlorine. So there's 1 iron on the left, there's 2 irons on the right. So I'm going to start the process of trying to balance the iron atoms. I'm going to put a coefficient of 2 in front of the FeCl₃ on the left. Now let's take a look at that table for the elements on the left and see how that 2 changes the number of irons and chlorines. So now the number of irons and chlorines would be 2 and 6 as a result of that coefficient. Now, since there are 6 chlorines on the left, but only 1 chlorine on the right, I'm going to try to balance the chlorine. So I'm going to put a 6 in front of the KCl on the right, so that way there would be 6 chlorines on the right. So here is the new total. That 6 affects both the potassium and the chlorine. So instead of 1 potassium and 1 chlorine on the right, now there's 6 potassiums and 6 chlorines on the right side of the equation. So how do I balance the potassium? There's 6 potassiums on the right, but there's only 2 potassiums on the left. So I'm going to use a coefficient of 3 in front of that chemical formula, K₂CO₃. So each of the elements in the formula K₂CO₃ has now been multiplied by 3. So with that coefficient of 3 in front of the K₂CO₃, this gives me 6 potassiums, because 3 times 2 is 6. I have 3 carbons, and then 3 times 3, that gives me 9 oxygens on the left side of the equation. I have 2 irons and 6 chlorines. And if I look at both the left side of the equation and the right side of the equation, I realize that now this equation is balanced. 6 potassiums, 3 carbons, 9 oxygens, 2 irons, and 6 chlorines on both the left side and the right side of the equation. So this equation is balanced with coefficients from left to right of 3, 2, 1, and 6. Now let's take a look at our next chemical equation, and the elements involved in this chemical equation are chromium, hydrogen, sulfur, and oxygen. So before I get started with adding coefficients, I can see that on the left side of the equation, there's 1 chromium, 2 hydrogens, 1 sulfur, and 4 oxygens. And on the right side of the equation, I see 2 chromiums, there's 2 hydrogens, and there's an SO4 inside parentheses, and there's a 3 on the outside of the parentheses, so that's 3 sulfurs, and then 4 times 3, the number of oxygens would be 12. Now, the first element I'm going to try to balance is all by itself on the left, and that would be chromium. So all I have to do to balance the chromium is put a 2 in front of the chromium. So now the chromiums are balanced. 2 chromiums on the left, 2 chromiums on the right. Now the SO4 is being multiplied by 3 on the right side of the equation. On the left side of the equation, I'm going to use a 3 as a coefficient in front of that chemical formula. And that would give me 3 sulfurs and 12 oxygens. Of course, it also changes the number of hydrogens as well. So my new total would be 6 hydrogens, 3 sulfurs, and 12 oxygens. Now the only element I still need to balance would be the number of hydrogens. So with 6 hydrogens on the left and only 2 hydrogens on the right, I'm going to use a coefficient of 3 in front of the H2 formula. So now that would give me 6 hydrogens. So 2 chromiums, 6 hydrogens, 3 sulfurs, and 12 oxygens. This equation is balanced, and the coefficients from left to right are 2, 3, 1, and 3. Now let's take a look at our next chemical equation, and the elements involved in this chemical equation are aluminum, oxygen, and hydrogen. So on the left side of the equation, I see 2 aluminums, and for the oxygen, there's 3 oxygens in that first formula, and there's 1 oxygen in the next formula. So with Al₂O₃, that's 3 oxygens, but there's another oxygen in the H₂O. So if you ever have the same element found in 2 different chemical formulas on the same side of the equation, you have to remember to pay attention to all of the places where that element can be found. So 3 plus 1, that's 4 oxygens on the left. And I see 2 hydrogens on the left. On the right side of the equation, I see 1 aluminum, and then since the OH, or the hydroxide ion, is inside parentheses, and there's a 3 on the outside of the parentheses, the OH is being multiplied by 3. So that will give me 3 oxygens and 3 hydrogens on the right. The first thing I'm going to do is try to balance the aluminum. So I see 2 aluminums on the left, and I would like to get 2 aluminums on the right. So I'm going to put a coefficient of 2 in front of the Al parentheses OH3 formula. This will give me 2 aluminums, but it also increases the number of oxygen and hydrogen. So on the right side of the equation, instead of 1, 3, and 3, I now have numbers of 2, 6, and 6. 2 aluminums, 6 oxygens, and 6 hydrogens on the right. Now I need to balance the hydrogen, and hopefully I can also balance the oxygen at the same time. So with 6 hydrogens on the right, I'm going to try to get 6 hydrogens on the left. So I'm going to put a 3 in front of the H₂O so I can get 6 hydrogens on the left. As a result of that 3, I now have 3 oxygens plus another 3 oxygens. So 3 in front of H₂O would give me 3 oxygens, but there's also 3 oxygens in the Al₂O₃ formula. So my total on the left side of the equation, 2 aluminums, 6 oxygens, and 6 hydrogens. Hopefully you can see at this point we have the same number of each type of element on both the left and the right, so this equation is now balanced. And the coefficients from left to right are 1, 3, and 2. Now let's take a look at our next chemical equation, and the elements involved in this chemical equation are calcium, chlorine, and oxygen. On the left side of the equation, I see 1 calcium. Now, there's a chlorine inside the parentheses, but it's being multiplied by 2 on the outside of the parentheses. So that would give me 2 chlorine atoms. There's a 3 for the oxygen inside the parentheses, and that's also being multiplied by 2. So 3 times 2, that would be 6 oxygens on the left side of the equation. So on the right side of the equation, I see 1 calcium, 2 chlorines, and 2 oxygens on the right. So the only element that is not balanced is the oxygen. So if there's 6 oxygens on the left, and I would like to get 6 oxygens on the right, I'm going to put a 3 in front of the O2. In order to balance the oxygen, that will give me 6 oxygens on the right. Since the calcium and the chlorine are already balanced, that was the only coefficient I needed. So there's 1 calcium, 2 chlorines, and now 6 oxygens on both the left and the right. This equation is balanced, and the coefficients from left to right are 1, 1, and 3. Now let's take a look at our next chemical equation, and the elements involved in this chemical equation are magnesium, oxygen, hydrogen, and fluorine. On the left side of the equation, I see 1 magnesium, and in that formula for magnesium hydroxide, the Mg and then parentheses OH2, I see 2 oxygens and 2 hydrogens in that first formula because the OH is being multiplied by 2. So there's 2 oxygens on the left. But hydrogen is also found in the HF formula, which is also on the left. So there's 2 hydrogens in the first formula, but there's another hydrogen in the other formula on the left. That's a total of 3 hydrogens on the left. And then I see 1 fluorine on the left. On the right side of the equation, I see 1 magnesium, there's 1 oxygen, I see 2 hydrogens, and 2 fluorines. So I have now counted the number of each type of element on the left and the right. And as far as where to start, I'm going to begin with fluorine because fluorine is only found in 1 formula on the left and it's only found in 1 formula on the right. So because there's 2 fluorines on the right, I'd like to get 2 fluorines on the left. So I'm going to put a 2 in front of the HF formula. So this will increase the number of hydrogens and fluorines. So my new total, I still have 1 magnesium and 2 oxygens, but on the left I now have 4 hydrogens and 2 fluorines. And the reason I have 4 hydrogens is because with that 2 in front of the HF, that gives me 2 hydrogens, but there's another 2 hydrogens in that magnesium hydroxide formula. Well, now I need to balance the number of oxygens, and hopefully this will also balance the number of hydrogens at the same time. So I see 2 oxygens on the left. I'd like to get 2 oxygens on the right. So I'm going to put a 2 in front of the H₂O so I can get 2 oxygens on the right. But with that 2, it also increases the number of hydrogens. So my new total for hydrogen and oxygen on the right would be 4 hydrogens and 2 oxygens. Now if I look at the left side of the equation and the right side of the equation, I realize that we have the same number of each type of element. 1 magnesium, 2 oxygens, 4 hydrogens, and 2 fluorines. So this equation is now balanced. And the coefficients from left to right are 1, 2, 1, and 2. Let's move on to our next chemical equation. And in this chemical equation, the elements that are involved are carbon, hydrogen, and oxygen. On the left side of the equation, I see 4 carbons in that first chemical formula, and I see 8 hydrogens also in that first chemical formula. Now, there's only 1 oxygen in that first chemical formula, but then I see O2. So the total of the number of oxygens on the left would be 1 plus 2, which is 3. Moving over to the right side of the equation, I see 1 carbon, 2 hydrogens, and in CO2, there's 2 oxygens, but there's also an oxygen in H₂O, so there's a total of 3 oxygens on the right. Now, as far as a good place to start to balance this equation, I'm not going to begin considering the oxygen. Even though the oxygens are actually balanced for the moment, those numbers of oxygens are going to change when I try to balance the carbon and the hydrogen. So I could begin with either the hydrogen or the carbon, because those elements are only found in 1 chemical formula on the left and 1 chemical formula on the right. So I'm going to start with the carbon. So I see 4 carbons on the left, and I would like to get 4 carbons on the right. So I'm going to put a 4 in front of the CO2. So that's going to change the number of carbons, and it also changes the number of oxygens. So my new total on the right side of the equation would be 4 carbons. I still have 2 hydrogens because that has not yet been affected with a coefficient, but now I have 9 oxygens on the right side of the equation. So 4 in front of the CO2, that would be 4 times 2, that's 8 oxygens, but then there's another oxygen in the H₂O formula, so that would bring the total to 9. So the next element I'm going to consider would be hydrogen. There's 8 hydrogens on the left, and I would like to get 8 hydrogens on the right. So I'm going to put a coefficient of 4 in front of the H₂O, so I could get 8 hydrogens on the right. So 4 times 2 is 8. So my new total, I still have 4 carbons, but now I have 8 hydrogens, and you can see that now the number of oxygens has been increased as well. So there's 12 oxygens on the right side of the equation. In the CO2 portion of the equation, 4 in front of CO2, 4 times 2 is 8, but now I have a 4 in front of the H₂O, so 4 times 1 is 4. So 8 oxygens plus 4 oxygens, that makes a total of 12. So now oxygen is the only element that needs to be balanced to finish off this equation. Now, even though there are 12 oxygens on the right side of the equation, which is an even number, I can't put a 6 in front of the O2 because there's an additional oxygen in that first chemical formula. So if I put a 6 in front of the O2, that would give me 12 oxygens plus 1 more, and that would be 13. So what can I do to get exactly 12 oxygens on the left side of the equation? Well, I'm going to use a fraction like I did earlier in this video, and that fraction is simply a temporary solution to the problem of balancing the equation, but then we know that there's a technique for getting rid of a fraction. So here comes the fraction. 11 over 2, or you could say 5.5. So 11 over 2 times 2 would give me 11 oxygens, plus 1 more oxygen in that first chemical formula. That would bring the total to 12. So now this equation is balanced, and the coefficients from left to right are 1, 11 halves, or 5.5, 4, and 4. But we're not done yet because we need to balance this chemical equation using the lowest possible whole number coefficients. So what I'm going to do now is make sure that I keep the equation balanced, but I'm going to make a change to each one of these 4 coefficients. So the first coefficient is a 1. I'm going to multiply that by 2. And now I'm going to multiply all of the other coefficients by 2 to make sure that it remains balanced. So 2 times 11 halves, or 2 times 5.5, would be 11. And on the right side of the equation, the 4 and the 4 are each going to get multiplied by 2, so those coefficients become 8 and 8. Now, is the equation still balanced? Yes, but now instead of 4 carbons, 8 hydrogens, and 12 oxygens, all of those numbers have now been doubled. So now I have 8 carbons, 16 hydrogens, and there's a total of 24 oxygens. But because this equation has the same number of each type of element on the left and the right, this equation is now balanced. And the coefficients from left to right are 2, 11, 8, and 8. Now let's take a look at our next chemical equation. And the elements involved in this chemical equation are aluminum, zinc, and chlorine. On the left side of the equation, I see 1 aluminum, 1 zinc, and 2 chlorines. And on the right side of the equation, I see 1 aluminum, 1 zinc, and 3 chlorines. So if 2 chlorines are on the left and 3 chlorines are on the right, I'm going to try to get the same number of chlorines on each side of the equation. The least common multiple of 2 and 3 is the number 6. So I'm going to do whatever it takes to get 6 chlorines on the left and 6 chlorines on the right. So I'm going to start with a coefficient of 3 in front of that ZnCl₂ formula, and that will give me 6 chlorines. It also changes the number of zinc. So now on the left side of the equation, I have 1 aluminum, 3 zincs, and 6 chlorines. Now to get 6 chlorines on the right side of the equation, I'm going to put a 2 in front of the AlCl₃ formula. So I can get 6 chlorines, but it also changes the number of aluminums. So now on the right side of the equation, I have 2 aluminums, I still have just 1 zinc, and I have 6 chlorines. So the chlorines are balanced, but now I need to fix the problem of the aluminum and the zinc. But since those are single elements, then I can balance the aluminum and I can balance the zinc without affecting any other element. So to get 3 zincs on the right, I'm going to put a 3 in front of the Zn, and then to get 2 aluminums on the left, I'm going to put a 2 in front of the Al. So now I have coefficients of 2, 3, 2, and 3, and I have 2 aluminums, 3 zincs, and 6 chlorines on each side of the equation. So this equation is now balanced. Let's move on to our next chemical equation, and the elements involved in this chemical equation are hydrogen, sulfur, aluminum, and oxygen. On the left side of this equation, I see that hydrogen is found in 2 different chemical formulas. So I see 2 hydrogens in that first chemical formula, H₂S, but then I also see an additional 3 hydrogens in that Al parentheses around the OH3, that aluminum hydroxide. So with 2 hydrogens in the first formula and 3 hydrogens in the second formula, that's a total of 5 hydrogens on the left. I see 1 sulfur, 1 aluminum, and again, because the OH is multiplied by 3, that would give me 3 oxygens in that formula. Now moving on to the right side of the equation, I see 2 hydrogens, there's 3 sulfurs, 2 aluminums, and only 1 oxygen. So I'm going to start with the sulfur. So there's 3 sulfurs on the right, and I have only 1 sulfur on the left. So because sulfur is found in only 1 chemical formula on the left and 1 chemical formula on the right, sulfur is a good place to start. I wouldn't begin by trying to balance the hydrogen because it's found in 2 different chemical formulas on the left side of the equation. So to balance the sulfur, I'm going to put a 3 in front of the H₂S formula, and this is going to change my number of sulfurs and my number of hydrogens. So my new total would be 9 hydrogens 3 sulfurs, and I still have 1 aluminum and 3 oxygens. So why do I have 9 hydrogens on the left? Well, 3 times 2, that would give me 6 hydrogens because of that coefficient of 3. And then there's another 3 hydrogens in that other chemical formula. So 6 hydrogens plus 3 hydrogens is 9. I'm not ready to balance the hydrogen just yet. So I'm going to balance the aluminum. I see 2 aluminums on the right, and I would like to get 2 aluminums on the left. So I'm going to put a coefficient of 2 in front of the aluminum hydroxide, or the Al₅OH3, that formula. And so now that is going to give me 2 aluminums, but it's also going to change my number of oxygens and hydrogens at the same time. So my new total on the left would be 2 aluminums. I now have 6 oxygens because I had 3 oxygens in that chemical formula before the coefficient was added. So now that's 2 times 3, that's 6 oxygens. What about my hydrogen? Well, I have 3 in front of the first formula. That would be 3 times 2 is 6. And now with that 2 in front of the next formula, 2 times 3 is 6. There's actually 12 hydrogens total on the left side of the equation. So what I'm going to do now is, hopefully, if I balance the oxygen atoms, it will also balance the hydrogens at the same time. So with 6 oxygen atoms on the left, I would like to get 6 oxygen atoms on the right. So I'm going to put a 6 in front of the H₂O on the right side of the equation. This will give me 6 oxygens, which is what I need, but it also gives me 6 times 2, that's 12 hydrogens on the right. So my new total on the right side of the equation is 12 hydrogens. I still have 3 sulfurs and 2 aluminums and 6 oxygens. Well, in this process of balancing the equation, I was able to get 12 hydrogens, 3 sulfurs, 2 aluminums, and 6 oxygens on each side of the equation. So this equation is now balanced, and my coefficients from left to right are 3, 2, 6, and 1. Let's take a look at our next chemical equation, and the elements involved in this chemical equation are nitrogen, hydrogen, phosphorus, oxygen, and calcium. Now, your initial impression of this particular chemical equation is it seems rather challenging. It seems rather intimidating to try to balance all of these different elements. We have 5 different elements on the left and the right. We also see that many of these chemical formulas contain parentheses, which presents a challenge in terms of multiplying and keeping track of all the elements. So after I go through counting the number of each type of element on the left side and the right side, I will show you that there is a much easier way to balance this chemical equation. So stay tuned for a much easier way to process and balance this equation. So first I'm going to count the number of each type of element. Starting with, on the left, I see nitrogen is found in the first chemical formula. It's inside parentheses, so that's NH4 multiplied by 3. That would be 1 nitrogen multiplied by 3. So that's 3 nitrogens, but then on the other chemical formula on the left, I see nitrogen is also found inside parentheses multiplied by 2. So the N in the calcium compound is multiplied by 2 for that formula. So 3 nitrogens and 2 nitrogens make 5. Again, don't worry. There's a much easier way to balance this equation. All right, let's keep going. I see hydrogen. There's 4 hydrogens inside the parentheses, NH4. That's 4 hydrogens, and it's multiplied by 3. So that would be 12 hydrogens on the left. There's only 1 phosphorus, so that's simple and easy. So 1 phosphorus. And for the oxygen, there's 4 oxygens in the first formula. And then I see NO3 multiplied by 2. That would be 3 oxygens times 2. That would be 6. So 4 oxygens plus 6 oxygens, 10. 10 oxygens on the left. and then only 1 calcium. Whew. Okay, don't worry, there's a much easier way to do this. On the right side of the equation, I see a nitrogen that's actually listed twice, so NH₄NO₃, so that's 2 nitrogens. There's 4 hydrogens, so NH₄. I see a phosphorus inside the parentheses, and it's multiplied by 2, so phosphorus times 2, that's 2 phosphorus. There's 3 oxygens in that first chemical formula on the right, and then I see PO4, that's 4 oxygens times 2 with the parentheses. So 4 times 2 is 8, so 3 oxygens plus 8 oxygens would be 11, and then 3 calciums. So as I said, there is an easier way to balance this equation. So instead of counting the individual atoms of each element, which is very challenging to do with this chemical equation, a simpler way to balance this equation is to focus on the polyatomic ions that appear on both sides of this equation. So here are some examples of polyatomic ions. This was something that I had taught earlier in the school year when I was teaching about ionic bonding. So you can see ammonium, NH4 plus 1, hydroxide, OH minus 1, and there's also chlorate, nitrate, carbonate, etc. So that first chemical formula that's listed on the left side of the equation is called ammonium phosphate. The next chemical formula that's listed on the left side of the equation is called calcium nitrate. And on the right side of the equation, I see ammonium nitrate, and then finally calcium phosphate. So how is this going to be easier for us to balance? Well, what I can do is count the number of ammoniums, the number of phosphates, the number of calciums, the number of nitrates. So I'm going to create a table that focuses on the polyatomic ions. And this will be much easier for us to keep track of as we're counting the components on the left side and the right side of the equation. So now instead of trying to balance the individual nitrogen atoms and oxygen atoms, I'm going to count how many ammonium ions, phosphate ions, calcium ions, and nitrate ions appear on the left side and the right side of the equation. So here's the count. 3 ammoniums on the left, 1 phosphate, 1 calcium, and 2 nitrates. Hopefully you found that was a lot easier than trying to count the individual nitrogens and oxygens. Now on the right side of the equation, I see 1 ammonium, there's 2 phosphates, 3 calciums, and 1 nitrate. Now with respect to where to begin, I'm going to begin with the phosphate. So I see 2 phosphates on the right, and there's only 1 phosphate on the left. So I'm going to put a coefficient of 2 in front of that first chemical formula. Now that 2 is going to change the number of phosphate, which is what I want, but it also changes the number of ammonium ions. So 2 times 3, that will give me 6 ammoniums, and then there's going to be 2 phosphate ions as well. Now I see on the right side of the equation, there's 3 calcium ions. So I'd like to get 3 calcium ions on the left side of the equation. I'm going to put a coefficient of 3 in front of that calcium nitrate formula. This will give me 3 calcium ions, but it also gives me 3 times 2, it's going to give me 6 nitrate ions. So on the left side of the equation, I see 6 ammoniums, 2 phosphates, 3 calciums, and 6 nitrates. There's only one more coefficient that I need to add, and that will complete the process of balancing this equation. So how do I get 6 ammoniums and 6 nitrates on the right side of the equation? I can do that with one coefficient. So by putting a 6 in front of the ammonium nitrate formula, that will give me 6 ammoniums and 6 nitrates. Hopefully you found that to be much easier than trying to keep track of counting the individual number of nitrogens and hydrogens and oxygens and so forth. So at this point, this equation is now balanced. I have the same number of each type of ion on the left and the right, and the coefficients from left to right in this balanced equation are 2, 3, 6, and 1. Now let's take a look at our next chemical equation. It's much simpler and more straightforward than the previous one. Hopefully you found that to be true. And so in this chemical equation, the elements involved are simply nickel and bromine. On the left side of this equation, I see 1 nickel and 3 bromines. And on the right side of this equation, I see 1 nickel and 2 bromines. Now, the least common multiple of 3 and 2 is 6. So I'm going to do whatever I can to get 6 bromines on the left and 6 bromines on the right. So I'm going to put a coefficient of 2 in front of that chemical formula on the left, and that will give me 2 nickels and 6 bromines. But now I just changed the number of nickels, so I'll fix that on the right. So I'm going to put a 2 in front of the nickel, and then put a 3 in front of the bromine, so that 3 times 2 is 6. So now I can see in this much simpler chemical equation than the previous example that it is now balanced. 2 nickels and 6 bromines on each side of the equation, and the coefficients from left to right are 2, 2, and 3. Now let's take a look at our next chemical equation, which is also very simple. It only involves 2 elements, phosphorus and chlorine. On the left, I see 4 phosphorus atoms and 2 chlorine atoms. And on the right, I see 1 phosphorus atom and 3 chlorine atoms. I'm going to begin by balancing the phosphorus. So if I have 4 phosphorus atoms on the left, I'm going to put a coefficient of 4 in front of that PCl₃ formula so I can get 4 phosphorus atoms on the right. Of course, it will also affect the number of chlorine atoms on the right. So my new total on the right would be 4 phosphorus and 12 chlorine. Well, the phosphorus is balanced, but to get 12 chlorine atoms on the left, I'm going to put a coefficient of 6 in front of the Cl2. So 6 times 2 is 12. So now that I have 4 phosphorus atoms on the left and the right, and 12 chlorine atoms on the left and the right, this equation is now balanced. And my coefficients from left to right are 1, 6, and 4. Okay, let's take a look at our next chemical equation. And the elements involved in this chemical equation are potassium, hydrogen, and oxygen. On the left side of this equation, I see 1 potassium, 2 hydrogens, and 1 oxygen. On the right side of this equation, I see 1 potassium. Now, hydrogen is found in 2 different chemical formulas. So there's H2, that would be 2 hydrogens, but there's also another hydrogen in the KOH formula. That's a total of 2 plus 1, so 3 hydrogens, and then there's 1 oxygen. Now, I'm going to show you 2 different methods to balance this particular chemical equation. The first method involves placing a fraction and then multiplying each of the coefficients by the number 2. So if you look at the left side and the right side of the equation, you realize that the only element that needs to be balanced is hydrogen. If I put a 1/2 in front of the H2 on the right side of the equation, well then that will count as a single hydrogen. So 1/2 times 2 is 1. And then there's another hydrogen in the KOH formula. So 1 hydrogen plus 1 hydrogen makes 2. This equation is technically balanced at this point, but I'm going to multiply each of these 4 coefficients by the number 2 so I can get rid of that fraction of 1/2. So my final coefficients would be 2, 2, And then since 2 times 1/2 is 1, that just goes away. That's understood to be a 1. And then finally 2. So I multiplied each of the 4 coefficients by the number 2, which means that now I've doubled all of the elements. So instead of 1 potassium, 2 hydrogens, and 1 oxygen, I've doubled those numbers. I have 2 potassiums, 4 hydrogens, and 2 oxygens. So that is one way to achieve the process of balancing the equation. I'm going to show you another way that will also result in this same set of coefficients. So starting over, instead of using a fraction in front of that H2 on the right, I'm going to recognize that I need more hydrogens on the left side of the equation. So why do I need more hydrogens on the left? Because right now there's 3 hydrogens on the right, and there's only 2 hydrogens on the left. So I'm going to put a number in front of the H2O, which is not going to balance the equation with one number, but it's simply going to increase the number of hydrogens on the left side of the equation. And I'm going to use a whole number to do this. So I'm going to use a 2 just simply so I can increase the number of hydrogens on the left. So as a result of putting a 2 in front of the H2O, I have 4 hydrogens and 2 oxygens. Now I still have 1 potassium on the left, so I'm not done yet. At this point, I'm going to try to balance the oxygen. And so by trying to balance the oxygen, that would be 2 oxygens on the left, I'm going to put a coefficient of 2 on the right. And I did this to get 2 oxygens on the right. But notice that by putting that 2 in front of the KOH, it also changes the potassium and it also changes the hydrogen. So here is my new total for the elements on the right side of the equation. I have 2 potassiums, I have 2 oxygens, and hopefully you can see why I have 4 hydrogens on the right side of the equation. So H2, that contains 2 hydrogens, but then the 2 in front of the KOH gives me an additional 2 hydrogens. So 2 hydrogens plus 2 hydrogens makes 4. Well, now the only element that I need to balance would be the potassium. So 2 potassiums on the right. Let me get 2 potassiums on the left. And now I have reached that same set of coefficients. I just didn't use a fraction to do it. So 2 different ways to achieve a balanced equation. So this equation is balanced with coefficients of 2, 2, 1, and 2. Now let's take a look at our next chemical equation. And the elements involved in this chemical equation are carbon, hydrogen, and oxygen. On the left side of this equation, I see 7 carbons, I see 16 hydrogens, and 2 oxygens. On the right side of this equation, I see 1 carbon, 2 hydrogens, and there's a total of 3 oxygens because the CO2 formula contains 2 oxygens, and then the H₂O formula contains 1 oxygen, so 2 plus 1 is 3. Remember that it's nice when you can balance an element that appears in only one chemical formula on the left and in only one chemical formula on the right. So I'm not going to begin the process of balancing this equation by starting with oxygen, because oxygen is found in 2 different chemical formulas on the right. So I'm going to start with carbon. There's 7 carbons on the left, and I would like to get 7 carbons on the right. So I'm going to put a coefficient of 7 in front of the CO2 on the right. Now this will also change my number of oxygens. So my new total for the elements on the right side of the equation would be 7 carbons. I still have 2 hydrogens because that has not been affected by this coefficient, but since 7 times 2 is 14, but I have another oxygen in that H₂O formula, I have 14 oxygens plus 1 more. That's why I have 15 oxygens total on the right side of the equation. I'm not ready to talk about the oxygens just yet because I'm going to focus on an element that's only found in one chemical formula on the left and only one chemical formula on the right, and that would be hydrogen. So because there are 16 hydrogens on the left, I'd like to get 16 hydrogens on the right. So by putting a coefficient of 8 in front of the H₂O, so 8 times 2 is 16, that will give me 16 hydrogens on the right side of the equation. It's also going to change my number of oxygens. So here's my new total for the carbons and the hydrogens and the oxygens. Now I have 7 carbons still, that's not been affected, but I have 16 hydrogens because 8 times 2 is 16. And as far as the oxygen, 7 times 2 in that 7 in front of the CO2, that would be 14 oxygens. And now with an 8 in front of the H₂O, that gives me 8 oxygens. So 14 oxygens from that first formula, 8 oxygens for that next formula, again including the coefficients. 14 plus 8 is 22. Okay, the carbons are balanced, the hydrogens are balanced, and now the only element that I need to worry about is the oxygen. So with 22 oxygens total on the right side of the equation, I know that I can put a single whole number coefficient in front of the O2, because that's the only place where oxygen is found on the left side of the equation. I don't need to use that method of using a fraction like I did in earlier examples. 11 times 2 is 22. So now I can see that with this set of whole number coefficients, the equation is balanced. I have 7 carbons, 16 hydrogens, and 22 oxygens on both the left side and the right side of the equation. So the equation is balanced with coefficients from left to right of 1, 11, 7, and 8. All right, let's take a look at our last chemical equation in this practice quiz. And this one is actually fairly simple and straightforward to balance. The elements involved in this chemical equation are potassium, oxygen, hydrogen, copper, and sulfur. On the left side of the equation, I see 1 potassium. Now, oxygen is found in 2 different chemical formulas. There's 1 oxygen in the KOH formula, and then there's 4 oxygens in that CuSO₄, or copper sulfate formula. So 1 plus 4, that's 5 oxygens total on the left. I see 1 hydrogen, 1 copper, and 1 sulfur. Now on the right side of the equation, I see 2 potassiums in that K₂SO₄ formula. The oxygen is found in 2 different chemical formulas. So in that first chemical formula on the right, the copper hydroxide, there's hydroxide OH is in parentheses multiplied by 2. So that's 2 oxygen atoms. But then there's also an additional 4 oxygens in the other chemical formula on the right. So K₂SO₄ has 4 oxygens. So 2 oxygens plus 4 oxygens, that would be a total of 6. Since the OH is multiplied by 2, that will give me 2 hydrogens. And I see 1 copper and 1 sulfur. So this equation is actually fairly straightforward and easy to balance. So watch what happens when I try to balance the potassium. I see 2 potassiums on the right, and there's only 1 potassium on the left. So I'm going to put a coefficient of 2 in front of the KOH formula on the left. Now this will not only give me 2 potassium atoms, which is what I wanted, it also changes the number of oxygen atoms and the number of hydrogen atoms on the left side of the equation. So here's my new total for the atoms on the left side of the equation. I have 2 potassiums. So now I see 6 oxygen atoms because there's 2 oxygen atoms as a result of that 2 in front of the KOH formula, but then an additional 4 oxygen atoms in the CuSO₄. So 2 plus 4 is 6, 6 oxygen atoms. There's 2 hydrogens because of that coefficient of 2 multiplying the chemical formula by 2. And there's still 1 copper and 1 sulfur. We'll take a look. Now I have the exact same number of each type of atom on both the left and the right. 2 potassiums, 6 oxygens, 2 hydrogens, 1 copper, 1 sulfur. So with a single coefficient of 2 in front of the KOH formula on the left, that's it. The equation is balanced, and the coefficients from left to right are 2, 1, 1, and 1. So this chemical equation that we have just balanced is the last chemical equation to balance in the practice quiz. So this is the end of the video. I hope that you found all of the answers and explanations helpful. Thanks for watching, and good luck studying for your quiz on balancing equations and classifying reactions.